Welcome back to another episode of Science with Surback. Today we're going to get a little bit more into the details of what chemistry has to offer. It should be a little bit of a review from a previous chemistry class. Now, before we get too far into the notes, just want to outline a couple of objectives that you should be able to accomplish by the end of it. The first objective that you should be able to accomplish is differentiate between the three states of matter. The second objective is distinguish between elements, compounds, and mixtures. The third objective is use the periodic table to determine the atomic number, atomic symbol, and atomic weight of an element. The fourth objective should be to define the terms group and period and recognize the common groups of elements. And then the fifth and final objective for you should be use the periodic table to determine whether an element is metallic, non-metallic, or a metalloid. So we start off here with how matter is classified. And for us, matter is going to be classified by two simple categories. The first of these categories is the state of matter. The second way we classify matter is by its composition. Now, the three states of matter, if we get into details here, are gases, liquids, and solids. And now some may say, hey, there's that fourth state with plasma, but for this class, we're not going to deal with plasma, so we're going to stick to those three states. And so we start out here with the first state, which is gases. Now, what we are going to do is we're going to break these things down into the microscopic level and also the molecular level. So, at the microscopic level, for gases, these states of matter have no fixed volume or shape. And because gases have no fixed volume or shape, they are going to conform to the shape of the container that they are placed in. Now, because gases are really far apart from one molecule to another, they can be compressed, or we can get those molecules closer and closer together because there's so much empty space in between each molecule. Now, I've already alluded to some of the things at the molecular level, but at the molecular level for gases, the molecules themselves are really far apart. Now, in between those molecules that are spread out really far apart in gases, all that exists there is empty space. And we'll get into more details when we start talking about the kinetic molecular theory and actually talking about a unit with gases as our focus. But that was something that really baffled scientists to begin with. It was, hey, there can just be empty space in between molecules. That's a really distinguished point for gases. The other thing at the molecular level is that molecules for gases are going to move at high speeds and they're going to collide often. Again, that second point we just wrote down is a very profound statement when we get to talking about something like the kinetic molecular theory and really getting into the depths and details of gases. So we move down here to our second state of matter, and the second state of matter are the liquids. And again, we're going to walk through first the microscopic level of liquids, and then we're going to move to the molecular level. So the microscopic level of liquids. Number one, this state of matter has a definite volume. The second thing for liquids is that they have no fixed shape. They're going to assume the shape of the container. And so if you think about that one, when you pour in a glass of water from one cup to another, whatever the shape of that glass is, that liquid is going to take that shape. And then the other thing at the microscopic level for liquids is that they're incompressible. So liquids get really, really close together compared to that of gases. And yes, those molecules still have enough space where they can slide by one another that allows it to flow or have that no fixed shape business. But they are very, very close together. And because of that, that does not allow them to be compressible. So they are incompressible. Now, at the molecular level, again, I already alluded to this earlier, but these molecules for liquids are much, much closer together than gases. They're right by each other. They still have a little room to slip and slide by each other. That defines that as a liquid, but they are so much more closer together than the molecules of a gas. And then the second thing with the molecular level of liquids is that molecules are still going to move rapidly. You're still going to have that movement of molecules, but they can slide past one another. So no longer do they have this big space where they're running all into each other like the gases. They're close together. They can still move relatively quickly, and they are sliding past one another. Again, they can move rapidly, but they're close together and they can slide past one another. All right, so we'll transition pages here and we'll talk about the third state of matter, which is that of solids. So again, that third state of matter that we will deal with in this class is solids. So once more, we start out talking about the microscopic level of solids. Number one, solids at the microscopic level have a definite volume and shape. And because solids have a definite volume and shape, they are going to be rigid. And if you want to think of rigid as locked in place, that's something really good to note or associate with solids. Now, solids are for the most part, even closer together than liquids. So because of that, there is almost no room for those molecules to move. So once again, these solids, just like the liquids, are incompressible. You cannot squeeze those molecules any closer together in solids. Now transitioning to the molecular level. So the molecules of a solid are so packed closely together that they're in these definite arrangements, or they form this nice pattern ordered structure. So we've talked about the three states of matter that we will see in this class. And now I want to have a little bit of a side note, and that is talking briefly about phase changes. So one state of matter can transition to another state of matter under two changes or under two alterations to their circumstances. The first of these changes that allows states of matter to go from one state to another is temperature change. And this is really simple to think about. If you take an ice tray and you fill it up with water, which is the liquid state of matter, and you put it into the freezer, well, it freezes, and because the temperature lowered, the state of matter now transitioned to a solid ice cube that you have. The other thing that can alter the state of matter or change from one state to another is a change in pressure. Okay, so we've talked about now the three states of matter, and that's one way where we can classify the type of matter we're dealing with. The other way that we can classify the type of matter that we're dealing with is based on the composition. So the first type of composition that we talk about or that we deal with in this class is that of pure substances. And so pure substances are defined as matter with distinct properties and a fixed composition. And so some things associated with this definition of a pure substance is that a pure substance is not going to vary from sample to sample. So what that means is that if I have a pure substance and I have it in the classroom here, and I have that same pure substance at my house, that is going to have the same composition. It is not going to change just because I drove to my house and have that particular pure substance. Now, some of our examples include things like table salt. And table salt is just sodium chloride, or as we'll get familiar with, it is NaCl. So that fixed composition of sodium chloride is always one sodium atom to one chloride ion. The other example is water. And water is always going to have the fixed composition of two hydrogen atoms connected to or bonded to one oxygen atom. Now, we can go one step further and break down pure substances into two distinct categories. The first of these categories that we can break pure substances into are elements. And we'll get a little bit more into details here, but just to give the basics, elements cannot be decomposed into simpler substances. The other thing to keep in mind with an element that's a pure substance is that they are only composed of just one type of atom. The other pure substance that we'll talk about are compounds. And now compounds, with a simple definition here, these are going to consist of two or more elements that are somehow connected or bonded together. Now again, a good example of this is water. And once more, water is going to have that defined ratio or chemical formula of H2O. And so no matter what, if I am talking about water, I am referring to something that has two atoms of hydrogen to one atom of oxygen. Now, something else to note is that this compound can consist of two or more of these same elements. Take, for example, pure oxygen. That is O2. Again, there's two atoms. They are the same element, but they are bonded together. So that's something to keep in mind. Now, what we're going to do, we're going to transition the other composition of matter, and that other composition of matter is going to be our mixtures. So mixtures are defined as a combination of two or more pure substances. And so because these mixtures have two or more pure substances, each of these substances is going to retain its own identity. And so because substances in a mixture retain their own identity, these mixtures can be separated. So a great example of this is a salt and sand mixture. Or if you're thinking about food, it could be a simple garden salad. And so something here, it's really easy to see with a salad, is that a mixture, again, because it has multiple pure substances, it can be broken down into those individual pure substances. So salad, let's say you make a salad, right? You put the lettuce, tomato, cucumber, whatever you like to put in there. You could actually physically separate each of those individual parts of the salad into their own pure substance. And that's what makes or defines what a mixture is. So we will get back to distinguishing between mixtures and pure substances and classifying these particular states of matter here in a second. But what we're going to do now is we're going to shift gears a little bit, and we are going to get into the periodic table of elements. Remember, this was one form of our pure substance. And it's really, really important to us here in chemistry. So the first thing that we have is this. Right now, there is 118 known elements on the periodic table of elements. And something else to know is that just because there's 118 elements doesn't mean all types of elements exist equally. These elements are going to vary quite a bit in abundance. So a good example of this is that oxygen, silicon, aluminum, iron, and calcium are going to make up over 90% of Earth's crust. Another really good example of how elements vary in abundance is what is in the human body. So in the human body, oxygen, carbon, and hydrogen make up about 90% of the mass of the human body. Now, each element that we have known is given a unique name and is abbreviated by a chemical symbol. Now, this unique abbreviation that we develop the chemical symbol for each element uses either a 1 or 2 letter symbol that is derived from its name. Now, all of these elements that are known, these 118 elements, are organized in the periodic table of elements. And that periodic table of elements is where we're going to go next. We're going to talk about some of the details of the periodic table. So we'll transition pages here, and now we can get into the details of the periodic table. So the first thing that we're going to talk about is the names and symbols of the periodic table. And so how I'm going to do this is I am going to draw one element from the periodic table of elements. And I'm just going to do so right here on the sheet of notes. So all I'm going to put in here is one example from the notes. I'll pause the video and then I'll re-show that with what element I chose, and then we're going to talk about each of those components inside each box of the periodic table. Okay, so the element that I have as our example is that with the element symbol K, or the name for the element symbol K is potassium. And all I did here is I just copied down from the periodic table what we would find on our particular chart. Now, I went a little bit more detail in the atomic mass, but we'll get into details about how and what we need to do with that. The first thing that I want to do is I want to point out the element symbol. And so the element symbol for our periodic table that we will use is found right here in the center of the box that contains the information for each element. Now, with our elemental symbol here, the element is represented by a 1 or 2 letter symbol. So with this symbol, the first letter of the elemental symbol is always capitalized. The second letter in the elemental symbol, if it has one, not everyone does, but the second letter to represent an element is always lowercase. And so we have to be very, very careful when we write the element symbols. So a good example here is this one right here. Okay, so I'm going to have capital C, little o, versus capital C, capital O. The one on the left, because it's an upper and then a lowercase, represents one single element, and that element is cobalt. The one on the right, because it's two uppercase letters, those represents two unique individual atoms, and this is actually a covalent compound known as carbon monoxide. So we have to be very, very careful when we write the symbol for our elements. Now, the next thing that is represented in this box for each element is this top number, and this top number is the atomic number. So again, I'm going to draw an arrow, and I'm going to start talking about the atomic number. So the atomic number, again, is represented at the top. It is a whole number, and very important here is this. The atomic number represents the number of protons in each and every element. Now, each element has a characteristic number of protons, or a unique number of protons. And so if we change the number of protons, we are changing the element that we're working with, or the element that we are talking about. So if we change that atomic number, or we change the number of protons, those numbers can be used interchangeably, we are changing what element that we are working with. Now, another important note here about our atomic number. In a neutral atom, so that means there is no charge, the number of protons is equal to the number of electrons. Again, just in a neutral atom, that means there's no charge. We're not dealing with an ion. Number of protons equals the number of electrons. The last item that we have to discuss on each box for the element in the periodic table of elements is this number here with the decimal. And so I know it'll be a little bit of a lengthy arrow here, but I'm going to bring this down. And this right here, this number, is known as the atomic mass. And so for our atomic mass, the atomic mass is the number below the element in the periodic table of elements. And now there is a way that we can calculate the atomic mass of each isotope, and that's an important thing to think about here. The reason that we have a decimal is that we have different isotopes, or we have a few different variations of that same element. And the variations exist from how many neutrons are in the nucleus of each and every atom of the specified element. That's why we have the decimal places, and we'll get a little bit more into detail. There's some calculations later in the year that we will talk about with the decimal places and things of that nature. But the formula for atomic mass, the atomic mass is equal to the number of protons plus the number of neutrons in the nucleus of the atom. And then our last thing that I want you to know is this. For our class, we will always round to 2 decimal places for the atomic mass. Okay, so we've had a basic orientation to what information is contained in each and every box of the periodic table of elements. And now what we can do is we can talk more specifically about the overall structure inside the periodic table of elements. And so what we're going to do, we're going to flip-flop back and forth between writing the actual written notes, and then I attached a periodic table, and so I'll talk about something, I'll write it down, and then I'll come over to the periodic table and write down whatever I talk about in that particular section of notes. So, number one, the periodic table is organized in a very meaningful way. And so the reason that it is organized in the way it is that it has periodic properties associated with the table itself. So that's why you see the U-like shape that the periodic table has. It's in that shape because we are placing elements in certain places where they align with properties of elements that are similar or around that particular element. So the first thing that I want you to note here, and that we will transfer to the periodic table, is that the periods are the rows, that's left to right, in the periodic table. So again, like I said, we're going to write this down, and then I want to label this on our periodic table that I've inserted into notes. So periods are the left to right portions, or the rows, in the periodic table of elements. So I'm going to draw a line with some arrows, and again, left to right. These things here are known as the periods, or if you want to think of this as rows, and they move left to right. Now, the second thing that I want you to know is that groups are the columns, or the up and down portion of the periodic table. And so again, we'll write this down, and then we'll go over to our periodic table, and we will use it to put that information here. So again, groups are the up and down portions, or the columns, in our periodic table. And so a couple of things with our groups, and we'll transition back to our notes here, but our groups for the periodic table there is several different numbering conventions, or several different numbering ways that we can go about naming the particular groups. The first way that you commonly see is numbering the groups 1 to 18. And I would say this is the most common. It's definitely the way I use it, but I will show you an alternative method after we write these down. So again, when we're talking about groups, they are the up and down columns, and if we're going to number it in a way from 1 to 18, what we're going to do, we're going to start here with the group with hydrogen, and we're going to call that group 1, 2, 3, 4, all the way over until we get to the end of the periodic table. Again, groups 1 through 18, and this, I would say, is my way of classifying groups. There is an alternative way. I want you to notice too, these inner transition metals down here don't get clumped into this particular group. So our other way that we can number our particular groups in the periodic table is from 1A to 8A and 1B to 8B. So again, this is the way I really don't often use, but I do want to show it to you on the periodic table of elements. So we'll shift over. Again, we're still labeling groups the up and down columns. And so what I am going to do to distinguish it from the other group numbering, I'm going to have a purple pen, and I'm going to label groups 1A through 8A first, and then we'll move to 1B to 8B, excuse me. Okay, so the first thing that we'll label is groups 1A through 8A. And these, because they get classified with this A tag, are known as the representative elements. So we start out here again with the group with hydrogen. This is 1A. Then we move over to 2A. And then what we do, we skip over our original groups 3 through 12. And so right here with boron, this becomes 3A, 4A, all the way over until we get to 8A. Now, those again are called the representative elements, and they get tagged with that A on the end of those numbers. The B numbering is a little bit goofy, and so what we do here, the group with copper up and down here actually gets classified as group 1B. The group with zinc up and down here actually gets classified with the group 2B. Now, we move over here with the group of scandium, and we begin with 3B, 4B, 5B, 6B, 7B, and we have to be careful right here. So, from iron, Fe, all the way to nickel, this whole set of 3 groups gets classified as 8B. Again, I don't often use that, but you sometimes will see those numbering conventions used to describe the periodic table in that fashion. So that gives you a little bit of a background on that. So we'll transition back to notes for a couple of more things, and then we'll continue writing on our periodic table of elements. So the next thing that we have to talk about is specific group names. So the reason that we give specific group names to certain groups in the periodic table is that there is some similarities between all elements in that group, and they're special enough to have these specific names. So the first group name that I want to go over is group 1A, and that is known as the alkali metals. Now, group 1A, I want to actually identify as my alkali metals, and so what I'm going to do here is I'm just going to highlight the periodic table. Now, one thing that is unique about the alkali metals is that they include every group 1 element except hydrogen. Hydrogen's actually a non-metal. So again, I'm going to highlight this in red, and then I'm going to move to our next set of elements. So again, in red, boxed in red, is going to be our alkali metals. And I'm going to shade it in just so we can distinguish it from other portions of the periodic table. But group 1A, this right here in red, is the alkali metals. Now, transitioning back to our notes, group 2A is known as the alkaline earth metals. And so again, I'm going to transition to the periodic table, and I am going to label or shade in the alkaline earth metals. So we go over here to group 2A, and I am going to shade it in green with the alkaline earth metals. So I come over here, I'm going to box in and shade so we can distinguish it from one group to another. And so again here, just so we know, what I shaded in green, this right here is known as the alkaline earth metals. Now, I'm not going to write this next set on the notes on the previous page, but what I am going to do is I am going to shade this in dark blue. It's almost a purple color. And this right here, this is going to span the next 10 elements. Goes over to zinc and then all the way down. And it has a big set of elements. This set of elements is known as the transition metals. So again, I'm going to shade it in just so you know it can be distinguished from another portion of the periodic table. But this stuff here that I'm shading in is known as the transition metals. And it's all of those B group elements. Once again, I'm going to shade it here in this dark blue, and these are known as the transition metals. Okay, another set of elements that I'm not going to write on the previous page of notes, but I am going to highlight here. These are down here. Okay, so down here, I'm going to highlight these in yellow, and these are known as the inner transition metals. And one thing unique about this, notice how there is a star and a little cross. These things, these 14 elements that are stretched across times 2 rows or periods actually get inserted right here with lanthanide and actinide. So if we actually put these in the periodic table, we'd have this big giant stretched out portion right there in the middle. And that's where these guys, the inner transition metals, fall. And the reason that they're typically not seen in that portion is it would make the periodic table look really awkward and wouldn't be as useful for us to utilize. So again, remember, these should actually be inserted into that portion. But again, in yellow here, in yellow, these things are known as the inner transition metals. Now, we move over, and once again, I'm not going to label it on the other set of notes, but we move over to this stair-step line. And so with this stair-step line, I'm going to start here with that of boron, and then I'm going to make my stair-step line all the way to here. So be very careful here. These are going to be the metalloids, but there's only certain elements here that I'm going to shade in. So I'm going to shade in boron. I'm going to shade in silicon and germanium. I'm going to shade in these next two elements here. And then the final element that I'm going to shade in is beryllium. Right here, element number 52. Those right there, these in orange are known as the metalloids. And again, they form the stair-step line, and they are known as the metalloids. Okay, so one thing I want to mention is this. Anything to the left, that's this way, anything to the left of the stair-step line, these things, and I'm going to draw an arrow, these things to the left of the stair-step line are known as a general classification as metals. Another general classification of elements is the stair-step line, which are metalloids. Now, I do want to transition back to our notes, and I want to talk about group 7A. So group 7A has a specific name known as the halogens. And so the halogens, what I am going to do here is I'm going to highlight these in a pink, dark pink color so that we have that labeled. So group 7A is the halogens, and all of the halogens are right here. Now, I shaded a little bit too far. It should just be fluorine down to iodine. But group 7A elements are known as the halogens. And again, that is a pink color. These are the halogens. Now we get to our final classification of our elements. And I do want to write this down on our other sheet of paper. And our final group that I want to write down is group 8A. So group 8A is known as our noble gases. So again, I want to label this. I'm going to label this in a light blue color, but our noble gases here are all in group 8A, and I'm going to label it as a light blue. And once again, the light blue are known as noble gases. Now, anything to the right of the stair-step line, these things are known as nonmetals. And then I want to talk about the things that are not highlighted. So right now here, these other elements that are not highlighted, it's not that they're not important, it's just they don't have a specific group name like the others did. So what I'm going to do, just in regular gray pencil, is I'm going to shade in these other elements. And these other elements, because they're to the right of the periodic table, these things shaded in pencil are known as the other nonmetals. Now, one thing that is special to this, notice hydrogen. Remember, I did not label hydrogen because it's not an alkali metal. It is classified as an other nonmetal, or at least we will classify it as an other nonmetal. Now we have these elements here that are to the left of the stair-step line, so that means that they are metals. And so for these, I'm just going to give them pencil stripes here, and these things here that are given as pencil stripes, these things are known as other metals. So again, not that they aren't important enough to have their own name, but these are the other metals. So I know this is a lot going on here, but these are how, or this is how we classify different things on the periodic table. So what we're going to do now, we are going to talk about, we're going to get back to compounds. We're going to go through one example of how to distinguish between something is a compound, mixture, pure element, whatever the class may be in that case. So we'll transition to the next set of notes here, and that is of compounds. So with our compounds, we start out with a simple definition here, is compounds are combinations of elements. Now, we've used an example before of water, and so we'll stick to that, but I'm also going to throw in one additional example. And so that additional example that I want to throw in is oxygen, O2. Now, notice how, again, it is the same element, but they're chemically connected. They have a bond in between them, so they can be classified as a compound. Now, if we have the opposite of a compound forming, which is what happened when water formed, we had two hydrogen atoms form a bond with one oxygen atom. The opposite of that compound formation is decomposition. Now, something unique with compounds is that they have different properties than their component elements. So an example here, water, H2O, is a liquid at room temperature. Whereas hydrogen and oxygen, if they're by themselves, they are gases at room temperature. Now, the last thing that I want to talk about with compounds is the law of constant consumption, law of constant composition, or the law of constant definite proportions. Now, what the law of constant composition states is that a compound always consists of the same combination of elements. And so I know we're running out of room here, but again, our example once more is water. So water is always 11% by mass hydrogen, and it is 89% by mass of oxygen. Okay, so now what we can do, we talk about compounds, we can talk about mixtures a little bit more here. And I know I ran into the mixture area, but a mixture is just defined as a combination of two or more pure substances. And so for each substance in a mixture, there are two things that are going to happen. Number one, it's going to retain its own identity. And number two, it is an overall component in that mixture. So the other thing to remember here with mixtures is that they can have variable composition. So an example of this variable composition is sweetened coffee. If you make your coffee at home, you may put 1 tablespoon of sugar in that cup of coffee, but if you go to Starbucks and you get a double mocha frappuccino, you may get multiple tablespoons of coffee. Both are sweetened coffee, but they have a different overall composition. Okay, so I ran out of room here on this page. So all I'm going to do is I'm going to get a blank sheet of paper and I'm going to continue writing these particular notes. So with a mixture, there's a little bit more to talk about, and that is the different types of mixtures. The first type of mixture is a heterogeneous mixture. And so a heterogeneous mixture does not have a uniform composition, properties, and appearance. And so a great example of a heterogeneous mixture is sand. So if you ever look really closely at sand on a beach, you'll notice that, hey, it has some different coloring, there's some different sizes, there's all of this business that is different from just one place on a beach to another. And so if you pick up a handful of sand out of one container, it may be a little bit different than a handful of sand out of another container. The other type of mixture is a homogeneous mixture. And so a homogeneous mixture is uniform throughout. And so some example of this include things like clean air in the Earth's atmosphere, vinegar, or some substance like Kool-Aid. Now, a homogeneous mixture can also be referred to as solutions. And so something to keep in mind with solutions is that they can either be a solid, liquid, or gas. All right, so we've gone back into details about compounds and mixtures, and we've talked in depth about elements with the periodic table. Now comes the point where we need to be able to take a piece of matter and we need to be able to identify if it is one of those things. Is it a pure substance? If it is a pure substance, is it an element by itself? Is it a compound? Is it a mixture? And if it's a mixture, what type of mixture is it? So what we do, or what I embedded into notes, is this particular chart. So this chart here, what we'll do is we will walk through this chart in our final example for today. So we have our example in notes of this. Aspirin, a common headache medication or pain reliever, is composed of 60% carbon, 4.5% hydrogen, and 35.5% oxygen by mass. Using this statement, we want to know, is aspirin an element, a compound, a heterogeneous, or a homogeneous mixture? So what we do here, we first say, hey, is it matter? Well, yeah, because it occupies space and has a mass to it. So now the first question that we ask is, we say, is it uniform throughout? So question one, is it uniform? Is it uniform throughout? Well, if you go and you get an aspirin from Walgreens or Walmart or wherever you get aspirin, it is going to be uniform throughout. There's not going to be inconsistencies in that pill, or else they would never get approval from the FDA. So the answer is, well, yeah, it is uniform throughout. It's consistent. And so if we follow this chart, we get an S. We have this. Does it have variable composition? Well, I just told you, no matter what, any aspirin that you pick up is going to have these percentage by mass. So the answer to that second question, does it have a variable composition, is no. So now that we chose no for that second answer, we move over here and we know, hey, it's a pure substance, but we want to know, is it a compound or an element? So we ask ourselves this final question. Can this particular substance be separated into simpler substance? So we ask ourselves, hey, is it composed of different atoms or elements? The answer is yes, it's composed of 3 different elements. And if you wanted to, you could actually break that particular compound into simpler substance. So because the answer is yes, we have a compound. So again, because that answer is yes, what this means about aspirin, what it means is that we have a compound, or it is a compound. So you can use that chart to be able to determine if something is a pure element, a compound, a heterogeneous or homogeneous mixture. All right, so I know this has been a little bit lengthy of a section of notes, but as always, I hope you have enjoyed it, and make sure you always subscribe.